Good afternoon, everyone. This is going to be a talk for non-modelers. I'm going to um, do an overview, not about uh, the models and their applications that are out there, but there's a lot of colleagues that hear about modeling and they would like to, and they are non-modelers, and they would like kind of a brief explanation of they would like a brief explanation about what a compartmental model is, because that's the most common type of model we use in tobacco control. And here we go. Um, Good afternoon. My name is David Mendez, and I'm a faculty member in the Department of Health Management and Policy at the University of Michigan. And today I'm going to talk about a type of models known as compartmental models. And I'm going to also give examples from tobacco control. So these compartmental models are also called aggregate models, and in the context of microsimulation, or in the context of simulation, they're also called macrosimulation models when the compartmental models go to a simulation. Um, so So, um, so I'm going to have a illustrate compartmental models with an example. So let's start assuming that we want to track the number of smokers in a population over time. The population is very heterogeneous, and individuals have multiple unique characteristics, including gender, age, gender, education, socioeconomic status, etc. But we are only interested in tracking their smoking status. So if that's the case, instead of having individuals represented with all their characteristics, we're going to only distinguish them by their smoking status. So we're going to have only, though instead of fully developed persons, I'm going to, because that's what I am interested in, I am going to simply classify them as never, current, and former smokers, whatever definition you might have of them. So individuals in each category are going to be indistinguishable from each other. So we can organize then those individuals in homogeneous groups and enclose them into buckets and that we can call also compartment. And at the very end, since all the individuals inside a specific bucket are identical, we are only interested in the number of people in each compartment. So we are tracking the number of individuals. In this case, we have 24 never smoker, 10 current smoker, and 4 former smokers. So, but maybe we want to distinguish them a little bit more. How about if we realize that individuals at different age in different age groups behave differently with regard to their smoking behavior? So we identify 3 age groups from 0 to 17, 18 to 24, and greater than 24. And we can call them, label them, experimenters, the younger group, the 18 to 24 initiators, and individuals with an established pattern greater than 24. So what we do with that, we simply create more compartments if necessary. So, but now we discriminate more about what we think is important in keeping track of those individuals in the buckets, right? The numbers in the bucket. So we then, record the number of individuals inside all the compartments over time, and that's what the simulation is, right? If we realize that we want to further divide the individuals given a certain age, let's say we want to distinguish individuals less than 50 and more than 50, then what we do, we simply, create more compartments. In the same way, we can distinguish individuals by other attributes such as gender and socioeconomic status. And if we think of those characteristics can influence smoking behavior, the important factor is that we believe that we need to be sure that the set of compartments we arrive to comprise all the important characteristics that are important to all important characteristics that are necessary to answer the question that we're trying to solve. So how do we track individual? How will we track those buckets or compartments or the number of individuals inside the compartments, right, over time? So what we have here, let's assume, is a snapshot. That is a snapshot of a present time. So those individuals are different in the age groups. And at one point in time, we took a census, and these are the number of former, never, and current smokers. But at this future time, this a snapshot could be like this one. And the question is, how can I anticipate? And that's what a simulation model does, right? One of the principal characteristics is that it can anticipate the flow, the transition, and the number of individuals within those compartments over time. So suppose then this is the snapshot of the future time. This is t+1. So how do we develop these transitions? Well, it's very simple and might sound trivial, but most dynamic compartmental models follow the simpler rule to project the future, and is that the future is equal to the present plus change. And it's a very simple rule that it helps the modeler just set up their simulation, right? So remember, let's say that in this case we're trying to anticipate the size of the compartments. We can try to anticipate something else, the number of people that die and the number of people that initiate. But in this case, it's just all the individuals in the compartments, right? So there's, for example, I'm gonna take the current smoker compartment and currently have 10 individuals. This is what we call the present, right? And then we, exercise or anticipate or recognize the possible change. Before the next period, the compartment can lose members due to smoking cessation and death. And we'll get new members to former smokers who relapse and never smokers who will start smoking, right? And that's how we arrive to the future. So we started with 10, we see changes, and simply did the math and arrived to the future. So we ended up with 13 smokers in the next period. And then the process repeats, taking the bucket with 13 people and now as the new present and moving forward. Here's again the whole picture. And by the way, and Ken mentioned this in his talk, these models are also known in general as the stock and flow models. The quantities of the quantity of whatever elements we are tracking inside the buckets are what we call the stock, and the transitions between compartments correspond to the flow. The flow can be defined in different ways. This is a very simple way to define the flow. They are expressed by constant rate multiplied by the appropriate stock, for example. The initiation is shown here as the one parameter called the initiation rate multiplied times the number of never smokers. So this, what we call initiation rate, we can think of the probability in a certain time that a never smoker, initiate, right? And if we multiply that times the number of never smokers, then we have the total number of initiators, right? And these, let's say in this case, the flow between never smokers and the smokers is regulated by an exogenous parameters and that we call initiation rate. And it can be constant or not. And that parameter can be affected by policy, right? So we want to create policies that reduce the initiation rate. If in this case, we either have a rule to anticipate how the exogenous parameters is going to change, or is constant. We treat it like constant. When we have fixed proportion, or even if we have time varying proportion, these are what we call Markov models. They are linear models, Markov models, and they are in many cases are very useful in representing, in catching the overall transition of a system, a behavior of a system. Now, but in some cases, we have a more complex way to define the flow. For example, in this case, the initiation rate is a function, can be linear function or not, of an exogenous parameter, that's the lambda that we saw before, and the number of current smokers. Because it can reflect an imitation component in the initiation rate, right? The more smokers, the more individuals that could be imitated by the never smokers. So the initiation rate, grows, right? Now the model also exhibits what we call the feedback loop. And so this happens, for example, here when the volume of the compartment, now the number of smokers influences the volume of the same compartment in the future. And that can be directly or indirectly through other compartments. So it's whatever number, but whatever quantities we have at some point it determines what we have in the future. So these are an exhibit of a basic compartment model that keeps track of individuals by age, gender, and smoking status. The initiation and cessation rates are inputs that can be affected by policies, and we have a specific death rates by age, gender, and smoking status, and then we apply the same process that I showed before. So it's a repetitive process. So there are many examples of compartmental models and applications. So we have status quo projections. I'm not intending for you to be able to read the abstract. It's just I'm putting that for illustration. This one published in the Journal of Preventive Medicine by Jamie Tam, working with a model to predict mortality among adults with major depression, and makes projection if a status quo, if the thing continue, what's going to happen, what's the trend, and what would be those quantities in the future. We have estimation policy effects, like for example, the David Levy, published in 2011, the ban, the influence, the future effect of mental ban on smoking prevalence and smoking attributable death. So I'm going to go quickly around this. This is a feasibility analysis that my long time co-author and Ken Warner mentioned, and he mentioned about challenging the healthy people 2010 goal. And so we have what if a scenario. This is a this is the an analysis that was published in JAMA by Holford et al., talking about trying to estimate what would be the effect of tobacco control policies. How many lives were saved between 1965 and 1964 and 2012 because tobacco control policy. There's parameter estimation, and finally we have the multi-product analysis. And just recently, David Levy and colleagues, they published the description of a model that they developed that takes into account both e-cigarettes and cigarettes. So this kind of modeling exercises have been done, right? All of them with compartmental models. So it's a lot. These are just a few examples, but the omission of I could have put 5 or 6 or 10 in each category. So now that we know that why they are used and who is using, how they are used, and the characteristic of a compartmental model. Let's talk a little bit about the limitation. I see 2 major limitations. One, they cannot fully represent the heterogeneity present on the population. So the individuals are very different. They are in many different gender, and some of them socioeconomic status, some of the rich, some are poor, some are men, some are women, and they are older and they are younger. So a lot of interesting characteristics that more and more and more with data collection, we are learning how important or not they are in modifying smoking behavior. Another thing that the compartmental models cannot do very well or cannot do is representing the or anticipating the non-random connections and interactions among individuals. So there way in which humans connect and form networks that can be dissolved in time and can be changing or can be changing also as people age and people change jobs or graduate from the university. So those connections determine in great part, I think, how it's how the smoking behavior, part of the smoking behavior can be diffused. So if a lot of people, if people then in your network starting to quit smoking, probably you are more likely to quit because all your friends are quitting smoking, something like that. So the closing thoughts, given that the modelers should recognize when heterogeneity and network effects are important enough to merit abandoning the aggregate approach, the compartmental model, in favor of an individual-based model. So that's the other type of models that Dr. Luke is going to discuss later, and in which we can, the compartments are compartments of one, if you want. Everybody gets a full set of attributes, and there are rules of engagement. What happened with two people connect, and what happens if a person of certain religion connect with another person of the same age of other type of denomination. So how the behaviors, how that opinions can transmit through diffuse to social network and change behavior. Also, another aspect, another comment that I would like to make, and this is a little bit of apart. Different researchers have used different models, and there's always the comment of the model that someone used can do this, and the model that someone used cannot do that. So no model is better than other if they answer the question that they were designed for. We should not think of models as canned tools. So any new question usually merits an appropriate revision of the model or maybe a remodeling. This model doesn't treat initiation rate appropriately in this population. You simply change it. So you can do with data and knowledge, you can do anything you want with the models. The idea is that your basic idea the skeleton, it's better to be somewhat recognized and validated, so people, stay, have confidence in your results. So with that, I thank you, and this is the end.